Okay, so this slide speaks about methods of analysis. So when you analyze a structure in order to obtain the forces and reactions, you have two main methods. So you have the elastic analysis and plastic analysis. So the main assumption with the elastic analysis is that member remain in the elastic region when subjected to the design factor loads. So what that is mean, when you apply your force, your structure deform. In the elastic analysis, we are saying that the moment you remove all of the loads that you initially applied, your structure will go to its undeformed shape. So there will be no permanent deformation that happened to the structure. Elastic analysis comprises of two main subcategories. So you can have first order elastic analysis, second order elastic analysis. So in the first order elastic analysis, you are happy to ignore second order effects, which I will come to in the next slide. And so your analysis is purely based on the undeformed geometry of the structure. The second order elastic analysis, you take into consideration second order effects, and the way you take them into consideration, so you have two ways to do that. And it's not, so the first method is basically you need to apply some moment magnification factors. So you obtain your results from the first order elastic analysis, you obtain your moments that you need to design your member for, and then you multiply them by CY and CZ factor, given that they should be less than 1.4. If they are not less than 1.4, then basically your only option is to perform a full second order elastic analysis. So as you can see on the two equations illustrated on the right hand side, these are the interaction buckling equations from the IS 800 2007. So you need to satisfy both of these equations. Plastic analysis, in this type of analysis, you are mainly looking for plastic hinges. So where do they form? And usually we are after having a weak beam, strong column. The reason is you don't want the plastic hinge to form in the beam, because that you don't want plastic hinges to form in the columns, because that will result in a catastrophic failure on the structure and brittle structure. So what are second order effects? Let's consider the cantilever column shown on the right hand side. You start with the undeformed shape of your column. You applied axial force P, which act concentrically to the centroid of the column, and you applied your horizontal force H. You cantilever column deform, so deflect laterally with an amount equal to delta. Your vertical force P is no longer acting concentrically to the column, and that will result in additional moment that you need to consider to act when designing the cantilevering column. The other component is the small delta, which is related to the deflection of the cantilevering column itself between the endpoints. And that will also result in additional forces that you need to consider. So basically, whatever frame you are designing, your job as a structural engineer is first to know whether it is classified as a sway or non-sway frame. And I will come to this in one of the next slides to illustrate how you do that. Once you establish that fact, you need to know, is it sensitive to second order effects or not? If it is not, you can safely ignore them and just carry on with your first order elastic analysis. If it is, then you know that you need to consider them. Going to the next slide, again, continuing on the topic of second order analysis, you can see on the right hand side image. So that is the initial state of the structure, undeformed. You apply your loads, your structure deflect laterally, and there is delta in here. If you take it into account, your lateral deflection will increase further due to the presence of big delta. And if you consider small delta due to member deflection, again, your lateral deflection will still increase further due to that. And therefore, your overall deflection is made up of a summation of the first order lateral deflection plus second order big delta plus second order small delta. And that will be your total deflection that you need to design your structure for. So how do you decide how sensitive your structure is to P big delta effects? Basically, by calculating something called lambda crit, which is the elastic critical load factor, against specific set values on the code. If it is bigger than that values, you know it is sensitive, you need to consider them. If it is not, then you know that, okay, you're safe, you can ignore them. So basically, the elastic critical load factor is the ratio by which each of the factor loads would have to be increased to cause elastic instability. So how much you need to increase your loads by to cause elastic instability of the structure. The lower lambda crit is, the more sensitive your structure is to second order effects. The higher, the better. The good news is that nowadays computer and analysis and design structural software are very powerful, and most of them enable you to carry out the full second order analysis. But again, you need to be mindful and you need to understand what the software is doing and not allow it just to make all the decision on your behalf. Goal at the end of the day is to make sure that the strength of the frame should not be affected by changes in geometry during loading. So speaking specifically about non-sway sensitive frames. So structural engineer get presented with a frame. The first decision is it a non-sway or sway frame? And to make this decision per IS 800-2007 clause 4.1.2, so non-sway frames are defined as those whereby the maximum deflection over a story height due to notional horizontal forces less than or equal. So basically the first step is I need to calculate my notional horizontal forces. I need to apply them on my structure, and then I look at the specific frame. The second decision is, does my structure have a cladding? Okay, it does have cladding. The second question is, did I consider the stiffness of the cladding as well as other sheeting panel in the deflection calculation? If not, then you are in bullet point number 1, and you need to check that the inter-story drift, which is the deflection at the top of the story due to notional horizontal forces, minus the deflection at the lower part of that specific story due to notional horizontal forces, that needs to be less than or equal to the story height divided by 2000. If it is, then you are dealing with a non-sway sensitive structure. Second order effects can be ignored. If you're dealing with a structure that is uncladded, or where you took the stiffness of the cladding or other sheeting panels in the deflection calculation, then your limit is HS divided by 4000. For all other cases, you should consider your structure to be a sway sensitive frame, and therefore you know that P delta effects need to be taken into consideration. Continuing on the topic of non-sway, you can see the right top image demonstrate the deformed shape. You can see inter-story drift are minimal in these kind of frames, and the IS 800-2007 defined them as one in which the transverse displacement of one end of the member relative to the other end is effectively prevented. So basically, P large delta effects are too small to enable the resulting secondary effects and moments to be neglected. So if you're dealing with multi-story building, you need to, as a rule of thumb, you need to make sure that the horizontal deflections obtained when you add in the independently braced bay, so in this case delta 2, are 80% less for the same frame when you take out the independently braced frame. And the other assumption is that you are assuming that all of the horizontal forces will be solidly resisted by the independently braced bay. Okay, going to sway sensitive, you can see the right hand side image show the deformed shape of a moment resisting frame. You can see that the inter-story drift gets significantly bigger in comparison to braced frames. So how do you deal with them? How do you design them? So the first step is assume they are non-sway. You apply your loads, you design the frame, you size your members. Second step, you add in the notional horizontal forces. Again, you resize the member if there is a need, and then you make a decision whether it's a sway sensitive or non-sway sensitive. Okay, once you made that decision, if there is a need to account for second order effects, you add them into the analysis, and then you resize your members accordingly. So this slide talks about sway sensitive frames. However, this is specifically when conducting a plastic analysis rather than an elastic analysis. Again, the IS 800-2007 clause 4.5.4 say that second order effects, in order to capture them when you carry out a plastic analysis, there are multiple ways. So again, the first decision you need to do is, am I dealing with a cladded building whereby the stiffness of the infill panels have been ignored? So you are in bullet point number 1. Second thing you need to check is your lambda crit divided by lambda p ratio. Is it greater than 10? Okay, therefore you know that you can account for second order effects either by A or B. And again, A and B depends on alpha crit by lambda P ratio. So if it's less than 10 in the first case, greater than 4.6, you can simply use amplification factor. You amplify obtained plastic analysis design loads. If it is less than 4.6, then that's it. You cannot even use the amplification factor. You must carry out a full second order analysis. If you're using with a structure that is uncladded or a cladded structure whereby the stiffness of the masonry infill wall panels and other metal sheeting panels have been taken into consideration, then you are in bullet point number 2. The second criteria you need to meet is lambda crit by lambda P greater than 20. Okay, so how do you allow for second order effects? Again, A or B, and A or B depend once again on the ratio of lambda crit by lambda P. So what is the elastic critical load factor, lambda crit? How do you calculate it? So as per IS 800-2007, clause B 3.1, this is the elastic critical load factor of a frame. And it is defined as the ratio by which each of the factor loads would have to be increased to cause elastic instability. And this is the formula, which is 1 divided by 200 phi S max. Phi S max is referred to as the sway index maximum value. So how do you calculate it? The first step is to calculate your notional horizontal forces, and then you add them to the gravity load combination, and then you apply them to your structure. And then for each load combination, you look at the horizontal displacement, and then you calculate the inter-story drift, which is delta U minus delta L divided by the story height. You substitute that into the lambda crit equation, you obtain the lambda crit. So you calculate lambda crit for each story level. Once you have that value, you need to consider the lowest value out of all the floor levels. And if you are performing an elastic analysis, if the lowest value is greater than 5, that's good news. That means you can account for second order effects using the moment amplification factor. If it is less than 5, then you must carry out a full second order analysis. You're not allowed to use the moment amplification method. Okay, so last slide, I'm going to touch briefly on the topic of computer modeling of lateral stability system. So you can see in this figure, we have a shear wall on one side, core, and another combination of combined shear walls on one other side. So you can either model them in full details as illustrated by the left-hand side figure, so using 2D element shell elements, or you can approximate them to 1D stick element representing each shear wall. So in the core, you have 4 shear walls that act together to form the core. You represent each shear wall component by its own individual 1D stick, and then you join them at the floor level by 1D stick beams. You do the same thing for the other combined shear walls. Another course analysis would be to say, okay, I'm going to represent the whole core with only 1D stick element. And the simplest of them all is to say, I'm going to represent all of my lateral stability systems with 1D stick element. There is no right or wrong answer. A structural engineer needs to have a clear understanding of what they are after. So what results are they looking for? Are they investigating global instability? Are they studying specific members in details? You need to consider things such as complexity of the model, how long it will take you to build the model, how big the size of the model is. I usually would go for grillage model or 1D element per lateral stability system. So the 2 figures in the middle would usually yield satisfactory results, and the model size would stay light, and that will result in tremendous saving in the overall time spent on building the model.